In this session, we're going to be looking at subresources and the role that they play on the web in security considerations between different applications. So welcome to lesson number 5. Historically, the web is what we might call composable, and you can see from this example of a popular website that emulates the style of old applications. The web traditionally is about building a website and including all kinds of resources on it. Now, in this particular case, I think all of these resources are self-hosted, but a lot of the times you have applications that are using resources hosted on some CDN or just some other third party, and they're taking all of those. They say, we'd like to embed these in some way to enrich the experience of our website and web application. And you end up with something like this, right? You have a page that is not just it's not just a document with text and with functionality to perform certain actions, but it's a composition built from many different resources, which may have many security implications for that application. So we're talking about sub-resources, and I tried to find a nice, concise definition of sub-resource. I didn't immediately find one in the HTML spec. That led me to the SRI spec, where I also didn't find a definition. I invoked the old LLM for, when I'm all out of ideas, and it cited the SRI spec, but upon searching this text, I didn't find it within the document. So I'm not sure if this is a formal definition, but I liked it anyways. It suits our purposes. So subresource is a resource that a document fetches to complement its primary content, such as images, scripts, or style sheets. Those are just some examples. There are more. Ultimately, we're talking about documents that are embedding other resources, and from the perspective of cross-app security, typically we're thinking about cross-origin. So let's first examine a little bit deeper what we mean by a sub-resource. One way of thinking about it is as a destination, and in destination here, we're not talking about what is the destination of like an HTTP request that you're sending to some remote server. We're talking about the destination of a resource as it's embedded into a document. So you might recall we talked about the fetch metadata and their associated request headers. Well, the sec-fetch dest header here specifies the destination of the resource. Where is this going in the document that is calling out to it? And according to the fetch API, a sub-resource request has one of the following destinations, either the empty string or one of audio worklet, font, image, JSON, manifest, paint worklet, script style, track video, or XSLT. And just for comparison, a destination for a non-sub-resource would be something like a document, something like an iframe, not a sub-resource, but a, I guess document level resource is one way to think about that. Top level resource. So when thinking about the risk of the composable web and sub-resources, we're thinking about same origin policy again, and what protections exist to protect one application from another. The problem with same origin policy is that there are a number of exceptions that exist in order to facilitate embedding of cross-origin resources. So in general, because of these exceptions, there are two classes of risk that can arise. The first is risk posed to applications that are embedding malicious resources, right? So you run an application, you're embedding a script resource from some third party. Well, you're now relying on that third party. There is an implicit trust association, and you'll recall that JavaScript runs in the same execution context as even your own first-party JavaScript. The second risk is posed by applications that are embedded by malicious apps. So applications that have and host resources, and malicious apps try to embed those resources in order to cause certain actions or extract information from them. And one note that we're going to get into a little bit here as well with this session is that client-side injection attacks like cross-site scripting and HTML injection, these are ultimately attempts to embed malicious resources directly into an application that were not intended to be there. So these kind of fall adjacent to these categories of risk, and that's why we're going to look at them to some extent as well, at least where overlapping security risks and mitigations apply. In the simplest case of a resource that you embed on your application posing some risk, we have resource hijacking. So if you're dependent on some third-party script, as an example, right? You take a script tag and you embed a script from some other site. Well, again, you are now relying on that resource being secure. You're relying on whoever owns it, whoever hosts it, maintains it. And it turns out that there's actually a lot that can go wrong in the full life cycle of that script and the process of it being embedded into your application. And so the risk is from the possibility that attackers can modify that script content in order to inject malicious content. Now, there's one traditional attack that is excluded from here. I'll just mention it briefly, and that would be the situation where you have an application, it's secured over a TLS connection, so it's encrypted over the network, but that application embeds unencrypted links to third-party scripts. So the browser of users using your site is still making unencrypted connections to third-party resources. And it used to be that attackers, via an attacker in the middle attack, could hijack and modify those. These days, browsers by default will, I believe, upgrade or block what is known as mixed active content, right? So this is active content like scripts on your page that are mixed in the sense that your site is using a secure connection, they are not using a secure connection. So that's less of a consideration than it used to be. So usually when we're thinking about this type of resource hijacking, we're thinking about can an attacker, modify the code repo where that JavaScript is stored, eventually having it propagate to some CDN, or is the CDN itself compromised? Is there some other attack along that chain, like web cache poisoning, that will result in the attacker being able to serve malicious content? And crucially, as I've mentioned, all applications that embed the script now run the malicious content in the context of their own origin. There is no way, and we'll talk about this a little bit, but there's no way really to isolate or limit the capabilities of JavaScript that you need to be able to interact with your page. So this type of attack where some script is being poisoned in some way by attackers, it's a very common pattern in card skimming attacks, often mage cart style attacks you'll hear of. And one of the things that for me is a personal annoyance is because of the impact of these, they're so widely reported. You can find all kinds of instances of organizations, including technical organizations, reporting card skimming attacks. And the frustration for me is that they're almost never mentioning what the root cause was. Was it a cross scripting attack? Was it, poisoning of was it like CDN compromise? It's very hard to understand what the actual root cause is. And that kind of sucks for us as attackers because it's useful to know the proportion of different types of attacks that are successful in order for us to know how to prioritize our time. So card skimming as a type of attack, it's not a root cause, it's a consequence. It annoys me. Something that I just thought I would mention because you'll see it a lot as soon as you start looking. So there is one way we can somewhat mitigate these types of attacks within an application, and that is through a mechanism known as sub-resource integrity, and it's exactly how it sounds. We're embedding some sub-resource, and we're implementing a mechanism to force the browser to check the integrity of that script. And this requires the script to be a static resource, right? It has to not be changing. It has to be static over time. And what we do when we load that resource is we add the integrity attribute, as you can see in the screenshot or in the code snippet at the bottom. And crucially, one thing that is often overlooked is that the resource needs to support cores for the browser in order to be able to compute the hash in order to compare it to the one that you've hard-coded in the application. And so if an attacker compromises that CDN or the code base, well, I guess in this case it would be the CDN because this is a static versioned file, right? So if there's a change to the code, it would be a different version. So if an attacker, well, let's say, hijacks a CDN, or they're able to conduct like web cache poisoning or something, and a different version of the script is returned to your browser will look and see that the hash is different than the one that the developer specified, and it'll reject the script. It won't be able to load. There are a number of practical challenges with this approach. Even though it is a best practice, And of course, you'll see that down at the bottom left here at Digital Boundary Group, we report findings related to this. One, active content included without content integrity protection. Another, of which there are a few variations of, but this one is a common one, Google Tag Manager use, which is the use of scripts that you actually can apply SRI to because they're dynamic. It will break how those scripts work. So some scripts that you might want to embed onto your application, they're dynamic and you can't even use SRI. You're just depending entirely on that resource being secure, which a lot of people do for Google in many different ways anyways, but nevertheless, there is still some level of risk posed there. So the assumption of SRI is that the first assumption is that the computed hash version is safe. And I'm pretty skeptical that developers that are using sub-resource integrity are really validating the security of those scripts. Right, they're already kind of forming a trust relationship with some CDN, right? Like let's say in the last example we have jQuery, and they look at that and they're like, okay, well, at this moment in time we trust jQuery and we trust that version of jQuery, so we'll calculate the hash, we'll slap it on there. They're not reviewing that code, the minified script of jQuery. There's no way, right? So probably what the worst case scenario would be that a developer makes that decision to trust this right after an attacker has been able to inject malicious content into it. Now, I suspect because of the popularity of something like jQuery, that type of exploitation would be identified relatively quickly and mitigated in the supply chain. But nevertheless, there's still that opportunity that can exist that can undermine the benefit of sub-resource integrity. And going even further, sub-resource integrity presents a conflict between security best practices and development velocity. So in addition to JavaScript resources needing to be static, it raises a conflict of you now have to, you now have this effort to verify whether a script is safe to apply sub-resource integrity to, but you might also have other security directives to update script versions to avoid vulnerabilities that are identified in older versions. And this life cycle sometimes needs to happen, this process needs to happen very quickly. So I think there's a strong tendency to automate this, right? As soon as the latest new script is released, make sure that it can be updated without issue, that everything integrates fine, and then just automatically compute and assign an SRI hash value. Like that probably is a practice that a lot of development organizations have taken on without necessarily fully vetting the content of those scripts. So there's a conflict there, and certainly there's a level to which automation can undermine the benefit of SRI. I don't know of any studies that have looked at the effectiveness of SRI over time in mitigating actual attacks. Nevertheless, theoretically it can, and it does, I think, require a little bit of mindfulness beyond just slapping a hash on a resource and calling it safe. Now, another limitation of SRI is that it can only apply to certain sub-resources. JavaScript, CSS, fetch calls. So there are other sub-resources that you might want to protect, but you can't with SRI. And if you are using an application that embeds a lot of resources from a third party, and so this is an example, eBay.com from a number of years ago. I think this is roughly, the date is on the link at the bottom. This is from 2005, so just over 20 years ago. This is what eBay looked like. And the main application was hosted from the origin www.ebay.com with HTTP, and the images were hosted from a different resource. Now, obviously, that's one controlled by eBay, and probably it's very easy to get an image-based CDN relatively secure and probably more secure than a more dynamic website, but you are still creating this implicit trust relationship. And so it would be nice to have a mechanism where, in the worst case scenario, if our CDN is compromised, we don't want attackers to be able to deface our website by changing the images that we're embedding. And unfortunately, we can't do that with SRI. So really all we can do is self-host those images, or just really make sure that we're using a CDN that we trust to be secure. Now at DBG, we do have a finding for this, external resource inclusion without validation, but we're not going to just be applying that to images hosted from a CDN because the risk is really quite low. The finding really only applies in special situations where maybe there is more likely an opportunity to be able to hijack those resources. And of course, defacement is a real thing that does happen, right? Defacement attacks. Here is just one example. There are many examples over time for various reasons, from political to commercial to just for fun. Now, there is one problem that really warrants a session on its own, and maybe I'll make one day. But this is one where you very quickly get into the weeds of the particulars of browser rendering engines like JavaScript engines and the JavaScript or ECMAScript language itself. And this unsolved problem is about the execution scope of JavaScript. If I have an application and I want to embed a third-party script that is hosted by a third party, oftentimes I only want it to do one very specific thing, or I only want it to have limited access to my document or to my resources. But when that script executes, it's got full permission to do anything. It's treated exactly like my first-party code that I'm running on my application within that origin. And so there's a really big risk to embedding third-party JavaScript, as you know from cross-site scripting attacks, right? Cross-site scripting attacks are the attempt to run JavaScript within that first-party origin, in which case you can do virtually anything that the user can do. And there's no way really to isolate JavaScript that is practical in most cases. So there are a few possibilities that do exist now. One is to isolate JavaScript in an iframe and apply sandbox restrictions to it as appropriate. Now, the challenge with this is that you need some re-architecture in order to be able to still accomplish what you hope to with that script and have it interface with your top-level document however you intended it to. And that could be quite complicated depending on what that resource is intended to do. And similarly, another thing you can do is isolate JS in web workers. And there are some libraries that appear to be dedicated to doing this for different reasons. The one I linked here, PartyTown, is more for performance, like offloading resource-hungry third-party scripts to web workers. So I'm not going to talk about that in depth. The one concept that you could really dive deep into if you're really curious about this is the ECMAScript realm, which defines the execution space in JavaScript. And there seem to be ongoing, although I question how ongoing these are presently, efforts to create standards for managing isolated realms. And just as one example, we do have the capability to do this already in the browser. So iframes, as an example, they do create their own JavaScript realm with an isolated JavaScript execution environment. But there's no way to, let's say, load an external script and say, okay, I only want you to have these capabilities, access to these APIs. There's no real effective and often practical way to do that. So the best that we can usually do is restrict the source of scripts we run and to also ensure their integrity. Now, we looked at the integrity already. Now we're going to talk about a mechanism to restrict their source. And that is content security policy, which is, I think, a little bit confusing because it does a number of different things. And some things it does well and is worth doing, and other things it does less so well. And there are also so many ways to configure it that this session is not going to be a full look at content security policy. Maybe I'll have a deep dive at another point, but I think there should probably be enough for anyone who is not super familiar to get started in understanding, and if you're an attacker, subverting content security policy. So the CSP, it's an HTTP response header primarily, I'll say. There are other ways to implement it. The preferred approach is using it as a response header. And you can use it to implement restrictions for embedded content, so sub-resources, inline content, embedding documents. So if another app wants to embed your document, you can restrict that. And it also can restrict certain outgoing actions, like form action, I think is the directive. I'll talk about that in a moment. The primary goal of content security policy is ultimately to mitigate cross-site scripting vulnerabilities by restricting the valid sources of script content that can ultimately execute. But it has other goals and uses as well. So one I mentioned around outgoing actions. CSP originally, and it still does have mechanisms for limiting the impact of client-side injection. So restricting outgoing actions like the origins that you can target with forms like HTML forms. But it seems to be that the present community consensus is that there's always kind of a way, once you have cross-site scripting, like once you can execute script, there's really always a way to find some way to make, escalate what you can do or make outgoing connections or perform actions to something. So CSP is really best thought of as a mechanism to prevent injection rather than to prevent the impact of injection, which is much more complicated to do. So at DBG, of course, we have a finding for when CSP is absent, which is missing content security policy. Quite straightforward. Just looking at the basics, CSP breaks down into a number of different directives that restrict sources by type. So, for example, script source, you can define what sources for scripts are okay, style source for styles, image source for images. Typical values include none. So if we set image source to none, that's blocking images. If we set it to self, we can load resources from our own origin. And otherwise, we can have an allow list of URLs to define external origins that we trust as sources for those types of resources. And there are a few additional unique values that apply in some situations, so primarily script, but also styles. That would be unsafe inline, which if you don't include this and you're using content security policy, you can't use script tags with JavaScript inline there without specifying a specific source that is external to that specific document. It also blocks event handlers and JavaScript URIs if you don't include unsafe inline. Including unsafe inline for script source lets you include those in the document. And as a result, because a lot of applications traditionally have a lot of inline script, it's very common to see unsafe inline permitted within content security policies, which of course largely undermines the efficacy, which we will talk about. Unsafe eval and also WASM unsafe eval, which permits WebAssembly. We're not going to go into depth on those. Just know that these pose their own risks when enabled. Talking about some special directives, we have default source, which acts kind of as a fallback mechanism. So if you don't specify specific restrictions for another directive, it will fall back to what the default is. There's also base URI, which poses its own risk. So if you have relative URLs, as the one shown in the example here, script source loading an on-domain URL that's relative, the base URI can redefine what those point to. And obviously that poses a risk if an attacker is able to modify that. The object source restricts potentially risky resources within like object and embed tags. And finally, we have the sandbox directive. And this is a very special one. It works similar to an iframe in that it sets for the returned resource a unique or opaque origin. We'll probably discuss this in future sessions. I think the most prominent or most effective use case is when you have some application that is hosting user uploaded content. That could be file uploads. It could be like some custom like single web page that they're permitted to have. This is a way to restrict capabilities in that specific document or specific response from an application. It's pretty widely known that the traditional approaches that developers take with content security policy are not effective. And probably the big reason here is that coming up with an effective policy was never a priority. Developers were tasked with, hey, implement a content security policy, and they focused on implementing one with little effort that ended up working. Not necessarily the fault of developers. They have their own incentives and directives, and of course, at the end of the day, they're trying to make applications that work, not applications that are as secure as possible. But nevertheless, this study, which is quite dated now, so I imagine the landscape has changed a little bit, but it identified that of the CSP policies that do exist in the real world, almost all of them were I'll say very bypassable, or there were at least theoretical bypasses that existed. And I'm going to list some of those bypasses now. So the first one would be an over-permissive allow list, right? You trust a source, some origin where users can upload any content. Well, that's obviously a risk. Unsafe inline or unsafe eval, obviously risky. JSON P presents a specific risky scenario. I'm not going to go into the details of that. If an attacker hijacks a trusted resource, obviously that undermines CSP. Open redirects on trusted domains can undermine CSP. Base URI abuse, JavaScript framework script gadgets. So if there are ways to execute scripts that are unique to JavaScript libraries that you're embedding on your page that would not be blocked by content security policy, CRLF injection and other types of attacks that actually manipulate the content security policy of an application itself. These are less common to see, but we still do see them from time to time. And if you're using nonces, which we'll talk about in a moment, in some cases there have been ways to exfiltrate them in order to conduct attacks against nonce-based content security policy. And so at DBG, we also have a finding for insecure policies, and that is the insecure content policy finding. So speaking about nonces and hashes, this is the preferred mechanism in order to secure the resources, the JavaScript and related resources that appear on your page. Hashes are quite simple. You generate hashes based on the content. Nonces are a little bit more interesting. The way that nonces work is that they are generated per response. So you need a cryptographically secure pseudo-random number generator in your application that generates a nonce that gets placed in the CSP header and gets placed in the corresponding locations where there are scripts that you want to allow list. And this has to occur every time a page is loaded. So you can imagine from a development perspective, it's probably quite burdensome and probably requires a little bit of re-architecting. I would hope that more modern web development frameworks make this a little bit more easy and natural. I actually haven't implemented too many strict CSP policies, so I'm not sure about how easy it is to do on the modern web. But the fact that we rarely see it, I think, is a good indication that for most situations, it is non-trivial or at least unknown. So in this case, as with the other content security policy rules, all of the rules are evaluated by the browser. So as in the image you see below, if we're setting a script source directive with a nonce, and you can see that the value of that nonce is kind of random in like leet speak, the corresponding script that specifies that nonce in the response will be permitted to run. But the other script that has some different value will not be permitted to run because it hasn't been allow listed with its own nonce. Now, in the example, obviously random is a stand-in for an actually random value that changes every time so that an attacker can't guess it if they find a cross-site scripting vulnerability. One other mechanism that's important to note is strict dynamic that permits trusted resources to load other resources. So you'll see that in the example on the bottom right. If you have a script that is allow listed with a nonce, then it can also load other scripts, which does potentially open additional risk to the application, but it generally is an acceptable practice, I'll say, is kind of the consensus. So if you're using the approach seen in the screenshot here, which of course you can look it up at web.dev/article/strict-CSP, then you are using what is known as strict content security policy, which is the most, perhaps one of the only effective content security policy implementations. And it has the following features. So no domain or URL-based allow list. You're not trusting entire other origins. All resources must be permitted using a hash or a nonce. Strict dynamic can be used to permit trusted resources to load other resources. Object source and based URI must be set to none. And one thing that you can do is you can set unsafe inline for legacy browser support. You might think that, oh, that's dangerous because it's permitting any scripts inline. But if you're using nonces, unsafe inline actually won't apply. So that only will apply for browsers that don't support nonces, which are insecure anyways. And honestly, probably the market share of those browsers that need this are so minimal that you don't need to implement it anyways. Um, so let's talk about one more bypass scenario and one that impacts the secure situation. And we've seen this type of thing actually many, many times. So consider at the top the HTTP response that contains a content security policy configuration. And in it, we're specifying a script source with a specific nonce. So only the script that has that nonce specified is going to be able to execute. And on the bottom, for once, we're not looking at client-side code. We're looking at PHP that's going to be rendered and then returned as client-side code. So actually, it is JavaScript, but embedded in it is the PHP that's going to execute. And you'll see at the top that the top of that script, that we are specifying the correct nonce here. Now, normally it wouldn't be hard-coded like that. This would also be a generated component on the server-side, in the server-side logic of the PHP. But we also have PHP code embedded right in the username. And in this case, it's taking the value of the username and placing it right in this JavaScript context. So assuming that attackers can inject into the username value, this is still vulnerable to cross-site scripting because they're injecting right into a script context, and that script context is already trusted with the nonce. There's no way for the browser to distinguish whether this was an attack or not. So that's one other relatively common bypass for even the most secure content security policies. And I mentioned content security policies. Policy has, of course, another feature which was mentioned previously, but here it is more in depth. That is the frame ancestors directive, and this is very different than the other feature of preventing cross-site scripting. So it's kind of interesting that it also is used in the context of content security policy. But quite simply, by using the frame ancestors directive, we can determine what other applications should be allowed to embed our site, for example, in an iframe. And of course, by site, I mean that specific page with that specific response. Crucially, and probably ideally in many situations, you actually want to have a CSP policy that is tailored per response, per type of page. Usually that's what you'll see from very secure applications is they'll have a way of determining the type of resource being served, and they'll have a content security policy that is appropriate for each of those resources or pages. So in this example, if we set frame ancestors to none, then our page cannot be embedded within an iframe by other sites. So it is the modern alternative to old anti-framing techniques, and it has more capabilities as well because it does support space-separated list of permitted origins if that's necessary. CSP reporting is an interesting feature as well that's worth being aware of. And this is a mechanism for when the browser encounters a violation. So it encounters a situation that it blocks, right? Let's say you have a content security policy that says no inline scripts, and a response is returned with that policy, and in the body is an inline script. Well, in that case, your content security policy is going to say, no, this script can't run, it's a violation. And if you have reporting enabled, what reporting does is it permits the browser to send a log of that error, of that violation, to a reporting server so that you can track those. And there are many different ways to do that. There's the now deprecated, but probably still works in a lot of browsers, report-URI. Then there's the modern variation, report to, and there's also a relatively new web API known as the reporting API. And there you can specify reporting endpoints in the response header, and then you can refer to those endpoints in the content security policy to tell it where to report to. There's also one CSP variation we haven't talked about, which is report-only mode. So you can also implement a content security policy that doesn't block anything. It only reports, which is a good feature for debugging whether your CSP actually works, because what you don't want to do is block legitimate resources that break your application. And that's honestly the primary function for reporting. Now, it's been claimed by people, including some who, let's say, have, I will say, incentives to promote it in this way, but I've seen a CSP reporting promoted as actually being able to identify attacks, and I've never seen evidence for this. I've never seen attacks identified and then quickly mitigated. Maybe there are cases, but the reality is if you're an attacker and if you're trying to develop an effective cross-site scripting attack against an application, and that application has a content security policy that you're trying to bypass, you're probably testing that in your own browser. And if you're testing your payloads in your own browser, then you're controlling what your browser does. So you can simply suppress the reporting requests, right? If you trigger a violation, you don't have to let your browser send the violation report to the owners of the application that you're targeting. You can simply suppress it. I suppose that the one exception for that would be where would be like blind cross-scripting scenarios, or any situation where you're sending a payload and hoping that it exploits some context that you don't control. But I still to this day have not heard of attacks being mitigated by CSP reporting. I think primarily it's a useful mechanism to identify violations that are functional in nature. And just for your interest, this is what those reports look like. So just an example, it gives you quite a bit of detailed information. And I think actually these can be further enhanced to provide more contextual information about the code that caused the violation. So because we're talking about content security policy, I think it's worth talking about trusted types, even though this wasn't really intended to be a session on cross-site scripting. But trusted types are somewhat related to content security policy. So trusted types are ultimately a modern web mechanism to protect against DOM-based cross-site scripting attacks. So these are attacks that result from dangerous interactions with the DOM, where typically you're taking string data that contains an attacker's payload, and you're using something like document.write to write it to the DOM in such a way that the malicious content from the attacker can execute, assuming it's like, an HTML/JavaScript injection. So when trusted types are enabled, the way that it works is that the browser knows all of those dangerous mechanisms, what we would call sinks, from a DOM-based cross-site scripting perspective, and it will stop accepting plain strings as values. So if you try to set inner HTML in this example to some string, and you have trusted types enabled, your browser says, no, that's not going to work here, and it blocks it. So the way that you enable these DOM interactions for your application to work is that you have to create a policy, a trusted types policy, in order to effectively neutralize the input, and your policy returns a trusted type object, and that object then can be used to be passed to these sinks to construct the DOM. So one big advantage of this is that you can centralize the neutralization or sanitization logic into singular policies, which make it a lot easier to identify violations where the browser blocks them, and easy to consolidate the logic that you use to neutralize the input. And I mentioned this was related to CSP. Well, that's because it's enforced with the content security policy header. So when you set the directive require trusted types for, you can enforce trusted types. And once again, at DBG, we do have a finding for this that applies in certain scenarios, and that is the trusted types not enforced, which really only gets reported for the applications that demand the most security rigor. Because it is a relatively new mechanism, and it is relatively complex. And I will say that from the current state of the applications and organizations that we see, I think most do not have the development cycles to go as deep as implementing trusted types. That's just where we are right now. I think what we'd hope for is that development frameworks find ways to implement them by default to require minimal developer intervention and reduce ultimately the complexity of development. So this is a classic example of client-side JavaScript, and let's say we have some user input, and you can see that in this case I'm just setting it to a static string. But if you do actually have a user input, that's going to be pulled from somewhere. And in this example, of course, it's a classic payload. And so the situation is you're using inner HTML, you set it to the payload executes. This is what trusted types is trying to prevent. So when you enforce it, you set the CSP header, and here we're setting it for a scripts. And in the client-side JavaScript below, we're creating a policy that we also see referenced. And the policy effectively is where we're implementing our neutralization logic. Now, this is the area where trusted types can go very, very wrong, in that it relies on the developers to implement this logic. And that said, there are more standardized mechanisms to do this, but it still requires the foresight to do this and to implement something robust, right? Because in this case here, the policy just very simply strips script tags, which is not sufficient, right? So it is possible still, even using trusted types, to implement it in a way that's not fully secure, as in this example. Nevertheless, this is what trusted types look like. So the policy is up at the top of the bottom screenshot. In the middle, we have the blocked scenario where once trusted types are enforced, we can't set that inner HTML to a string. And in the bottom, we have a situation instead where we are setting internet HTML to the sanitized content. Okay. Now we're moving on to another type of sub-resource attack, I'll say, and that is cross-site script inclusion, otherwise known as XSSI. So embedding external scripts does result in their execution within the loading origins context, as we know, but scripts may also be loaded with users' authority with a third party, and that's ultimately where the risk arises from cross-site script inclusion, in that there are applications out there that have JavaScript content that contains potentially sensitive data, is maybe built dynamically in some way, and in many cases, if you are authorized to that, if a user is authorized with that application, let's say they're using cookies, and same site is permissive enough to permit that cookie to be sent cross origin, then you can load sensitive JavaScript cross origin. Now, you can't actually read that JavaScript, right? This is one of the protections offered by same origin policy, but JavaScript that we embed in our application is still rendered. So there is still interaction between JavaScript that we embed, even if we can't read it directly. And so there are many ways that we might be able to indirectly extract information from something that we embed with script tags. And that ultimately is the core of what cross-site script inclusion attacks are. And oftentimes, these attacks attempt to abuse JavaScript resources that contain sensitive information, but there are other alternatives to this as well. Just looking at some of the information leaking mechanisms. So if you set global variables or functions within a script that contains sensitive information and exposes sensitive information via those, that's something that can be accessed from an embedding site. Prototype pollution / what you might see referred to as monkey patching, loading pages. These are situations where the page that loads or like embeds the JavaScript poisons the prototypes of objects used by the loaded script, and we'll look at an example of that in a moment. Errors that occur from embedding scripts can sometimes leak information if you have a way to identify information about those errors. There are also side channel attacks with respect to resource loads. If a resource for some reason takes longer to load in one scenario than another, well, you can investigate, you can examine that loading time, and you can determine the state of that application, and that might leak interesting information. You can also monitor global side effects. Remember, because an embedded script runs in the full execution context of your document, it can modify your document. So if a script that you embed just by nature puts sensitive information in your DOM somewhere, well, your script can read that, right? That's like a shared interaction space, even though in theory those scripts should be separated by same origin policy, well, to certain degrees, I'll say. And of course, we also have JSON-P, which I think, as you already know, is just an insecure, out-of-date paradigm, which can also be abused in certain ways. So one case that we'll take a look at is the cross-site script inclusion using the prototype pollution approach. This, I believe, this simple case is obsolete in modern browsers. And with these types of attacks, that's one thing you'll see a lot. There are a lot of old school techniques, a lot of popular techniques that are obsolete in modern browsers. Besides just being obsolete, there are, of course, many additional considerations that you won't see when you're looking at old school XSSI exploits, things like same-site cookies. So cookies are not as permissive as far as when they're sent these days, and that can make attacks much more difficult in practice. In this particular case, though, I do think it's worth examining some of the older techniques to understand where we're coming from as far as a class of attacks. So in this case, let's say we have a sensitive script that we are going to embed, and let's say that it has some array there. At some point, it's going to create that array with those sensitive values, right? So the amount of money that the user has in their bank account. And I guess we're assuming in this case it's also, even though we're only looking at that one line where it's creating that array, we're assuming it's not being set globally, so we can't just access it that way. So below is a script that you might have on your malicious application. Of course, down at the bottom, we can see where we're loading the target script that contains that sensitive data, which, again, JavaScript should not contain sensitive data like that. Like, that's the primary mitigation here. Don't be doing that. But looking at the exploit, what we're doing is we're redefining, excuse me, we're redefining how arrays work in JavaScript in order to leak that information. That is effectively that attack. And browsers now don't allow us to do this, but they do allow us to do a variation, excuse me, and the variation that seemingly is still valid. Now, this seems to be valid based on my research. I haven't tested this. It's always a good idea to test it. I'm sure there's some resources out there that keep track of modern techniques that work, but I haven't seen many great ones. Anyways, in this case, we create a secrets array on our site that we want to protect the data of, and then we use secrets.push. And here, what we're doing is we're using a method call as opposed to a literal. And so the malicious application now, in this case, redefines that method. And just as before, it just adds console.log to log that data. Of course, you could do anything else with it with an actual attack. Again, I think this might work in modern browsers. It might be restricted, but the vastness and complexity of JavaScript is such that there's often a clever way to extract data in these kinds of situations. Here's a very or a relatively recent case study from obviously a bug bounty on HackerOne, and this was on Twitter, where there is a JavaScript file, and that JavaScript file just contained the user's ID, and that allowed the attacker to identify a cross-site script inclusion attack that could extract that user ID when that resource was included as a script from a malicious site. It's not the most impactful, but it does allow you to, if you could coerce an authenticated user on Twitter to visit your malicious site, you can extract that value and you can determine, what their Twitter account is, right? So there's value there in de-anonymizing users, and a lot of these types of attacks do things like that. Now we're going to look at a couple of historic examples, and these examples are interesting because they don't involve JavaScript, and that's obviously important to consider. Our attack surface is not just JavaScript. This first example is a CSV file, and crucially, it does not. Let's see. Well, this is actually, so this specific attack is no longer viable. It is historic, and actually, it was in Internet Explorer, by the way. So quite old by today's standards. Although it was reported in 2015. I guess that's over 10 years ago now. Time does fly. So if you look at the top, you see the response from the application. It's CSV, right? It's comma separated values. In the bottom, we're doing two things. We are creating a script on our malicious origin that creates or that redefines the error function in order to alert it. And then all we do is we embed the target script. And by doing that, the browser tries to interpret that CSV content as a script. And as a result, it sees those values as variables that are undefined. And so it leaks them. It leaks their names, right? So this is one attack where we can, under certain situations, leak information. Another very interesting example can occur when a character set is not specified. So this is a little bit more of a complex situation. If you look at the top, the setup for the attack is very similar. The only addition is the car set attribute, which is specified to be UTF-16BE. And in the response is different in that this is no longer CSV. This is a JSON object. And so we have a number of key value pairs in JSON. And what the outcome of this is that we get a different error message. And the error message we get is uninterpretable to us. It says characters we were not expecting is undefined, because what we've done is we've redefined the character set under which the target resource is to be interpreted by the browser. And what happens as a result of that is the browser, trying to interpret it as a script rather than recognizing it as JSON, what it does is it again sees an identifier that hasn't been defined, and so we get that error. Except all that content is that one big identifier, and that works because of the specific encoding that we can then decode. Right, when we get these values from the error message, we can go back and we can decode what that content was. Now, browsers are a lot more restrictive to prevent against these kinds of attacks than they used to be. So here's a very simple example. I'm trying to load, my site as a script, and it's blocked. And in this case, the big issue is actually that the X content type options no sniff is specified. And so the browser is like, I'm not going to try to interpret this as anything other than text/HTML, which is what's specified. So that fails. But in general, a content type of application/JavaScript is not required in order to coerce a browser to try and interpret a resource as JavaScript. The behavior now ultimately depends on a modern mechanism that we call cross-origin read blocking, or CORB, and it actually has a very complex set of rules. So if the content type is a protected type like JSON, HTML, XML, and the initial bytes, so CORB performs a confirmation sniffing. It tries to look at, based on the first few bytes of the body, what the content really is. If that matches, and if the content type is a protected type, it won't let you load it as a script. It will become an empty string. So as one example, if you have a document, if you have a resource that responds with the content type text/HTML, and it has a response body beginning, angle bracket HTML, well, the response cannot be embedded cross-origin. The browser is going to block that using its confirmation sniffing with CORB. So the content type header is strictly enforced with the addition, however, of X content type options no sniff. So we can also grant further protections against confirmation sniffing or content sniffing by adding the X content type options no sniff response header. And this is kind of an old school header. You've seen it applied in a lot of old, this has been reported by pen testers for the longest time. It works differently now than it used to work, kind of similarly, but nevertheless, it remains a best practice as long as, presuming you're indicating the correct content type, which you should be. So let's talk about CORB a little bit more. It's ultimately an algorithm that looks at the response and applies an algorithm in order to block dubious cross-origin resource loads. It's kind of like applying same origin policy to some of the original exceptions that exist in same origin policy, right? It almost is strengthening the protections of same origin policy. And the way it works is it blocks the response before it's even rendered in any way in the browser. And crucially, it can be very effective at blocking non-JavaScript-based cross-site script inclusion. So when it acts, the response body is made empty and headers removed. There is nothing that you can infer about that resource. There are some things that are exempt, so navigation requests or requests with a destination of object or embed, such as iframes. And as I mentioned, the protection is enhanced with the inclusion of X content type options no sniff. There's an explainer that I link at the bottom, which I actually highly recommend reading. You can learn about all of the logic of it and how it works. It's quite a well-written document. It's a nice guide to cross-origin read blocking. Okay, but we also have another mechanism that can help us protect against these types of attacks, and that is cross-origin resource protection. So this is a relatively new browser mechanism that lets us set a per resource policy that allows the application to selectively opt in to prevent resources from cross-origin no-cores requests. So unlike leaving it up to Corb to evaluate, this is a situation where if we have a certain resource that we know is sensitive for some reason, we don't want anyone loading it cross-origin, we can just say with cross-origin resource protection, don't do it. You can't have it. So it can have values such as same site, which I think is probably quite intuitive, same origin, as well as cross-origin, which of course would be the permissive case. So same origin would be most restrictive, cross-origin would be most permissive in terms of what can load and embed that resource via a no-cores request. I think this should all be familiar by now. It can also mitigate, in addition to cross-site script inclusion attacks, Spectre-like attacks, which are a little bit outside of the scope of this session. Notably, it doesn't prevent the request. Of course, it's a response header, and when browsers read the response, they see that header and they apply the rules then to determine whether to protect it. But it doesn't prevent requests from being submitted from the browser. So looking at the sum total of mitigations for cross-site script inclusion, of course, the first is set a proper content type. That should always be the case. Return well-formed content and be mindful of injection possibilities into that content. Enforce strict Corb via X content type options no stiff. Restrict resource read/embed capabilities to the extent possible with Corp. And finally, this has always been the case, it's never a good idea to embed sensitive content in JavaScript in the first place. Since we're talking about these modern security mechanisms via HTTP response headers, it's also worth talking about cross-origin embedder policy, though it's a little bit different and has much more limited security benefits. So COEP, if you will, is a document-level HTTP response header that mandates that embedded cross-origin sub-resources are corp or cores permissive. That is, when you set it on your application, when it's returned in the response on a document that renders your app, for all of the resources that you've decided to embed, it says we will only embed these resources if the corp policy or the cores policy permits us to do so, or is permissive to do so. So this ensures that sub-resources that you're embedding were intended to be embedded. It doesn't really impact a lot of attacks outside of, I think, really obscure situations. I think primarily it can be useful to enforce the thoughtful inclusion of embedded resources. So if you're a developer embedding resources in an application, implementing a COEP ensures that you will get an error if you embed something that maybe wasn't intended to be embedded in that way. And because we've mentioned these modern security mechanisms, it's worth talking briefly about site isolation. So I mentioned we're not talking about Spectre in depth. Maybe we'll do that in a future session. Ultimately, it's a situation where if you have rendered web content from that shares a process, if you have malicious content sharing a process with trusted content, there is a potential exploitation vector with the right mechanisms available to them because of speculative execution. So there's been an increased effort to create situations where there is isolation between trusted and malicious content on the web. And site isolation ultimately is a mechanism that doesn't, when you achieve it, it doesn't give you further protections. It's because you achieve it by implementing protections that certain dangerous features that browsers restricted at the onset of Spectre are now made available to you. So just as one simple example, in modern browsers, really precise timing features are disabled by default without site isolation because it could potentially be abused to exploit hardware-level vulnerabilities to read sensitive information within the same process from cross-origin resources that are embedded in that process. And if that all is very confusing, I apologize for that again. Maybe I'll do a session on this in the future. But it was worth mentioning because we talked about the actual mechanisms. So ultimately, to achieve site isolation, you have to have co-op set to same origin. Sorry, you have to have co-op set to same origin. You have to have co-ep set to require corp or credentialless. And due to co-ep being set, the embedded resources that are on your site naturally also have to be CORS or corp compliant to be embedded in that co-ep configuration. All of those considerations don't really come up day to day in application security testing, but if you're curious, definitely would recommend reading more about all of those mechanisms. So finally, since mostly we talked about as far as unique vulnerabilities, cross-site script inclusion, decided to include a slide on testing processes. Ultimately, you're looking for a resource that returns potentially sensitive information. Typically, that's going to be dynamic and tied to a user session. So you're also going to need a way to invoke that session, like cross-origin, so permissive cookies or something else. One thing that came to mind is sometimes there are internal resources that just implicitly trust certain sources, like internal IPs. So if you're in a situation where you know of a sensitive application that the access controls that are protecting it are simply by it being hosted internally, it might make a good target for XSSI, but it's probably really hard to actually find those situations in practice. In addition to containing sensitive information, obviously it must be you must be able to embed it cross origin as well. And the trick that you're trying to play if you're working with non-JavaScript is try to trick the browser into interpreting it as JavaScript. So consider the resource and how it sets the content type, what the configuration of corp or with NoSniff is, whether there are any encoding quirks, whether corp is set, and you also, in that resource, then need a way to cause some type of data leak, right? It's not enough to have an authenticated request to get a sensitive resource and embed it onto your site. Then you need to figure out, okay, how do I actually get the sensitive information from that? Is there a global exposure of a variable, some function call that you can rewrite, a DOM manipulation that you can observe happening, some type of timing condition? Ultimately, I think these are all the reasons, especially on the modern web, why cross-site script inclusion is quite rare to see. There are so many preconditions, there's so much to think about, and it's very hard to identify an exploit. And often from a security testing perspective, the reality is there are just other ways to prioritize your time. If you find one, super cool. But if you're not finding these types of issues, I wouldn't say that there's a huge gap in your testing processes necessarily, but it's worth being aware of. Okay, finally, and this is not even comprehensive. I think there may have been some that I missed, but I'm going to do an ASVS session sometime in the future. But these were some of the ASVS requirements that came up from all of the content discussed today. Excuse me. 1.3.3, verify that data passed to dangerous context is sanitized. So this, in my mind, is an area where trusted types could apply. 3.2.1, prevent rendering of response content in unintended contexts. 3.4.4, implement X content type options no sniff. 3.4.7, implement CSP reporting. 3.5.7, do not include authorized data in script content. 3.5.8, permit loading of authenticated resources only when intended. And finally, 3.6.1, implement SRI where applicable. So these, of course, are all summarized. They're simplified versions of the actual ASVS requirements. Highly recommend looking through that. And if you really want an exercise to learn more about the ASVS, try to find the requirements that I almost surely missed in summarizing, in finding all of the applicable ones to this session. And that's it for this session.